looking? Am I audible to you? Hello?
Yes,
Yes,
sir.
sir, you are audible.
Yes. Okay, and you can see my screen, right? So we'll be looking at a single pole at the origin. Ls is equal to 10 by s. So we have our s as equal to 5 e to the power I theta, and Ls is therefore equal to with a minus sign. This is very, very important. So when we plot this, what are we going to see now? We are going to have our circle as before. This is my input. So this is my input, and on the output side, this radius is 5. I'll now see a smaller circle. And the important thing will be, if this is how I am moving, in this case, how will I be moving? If I move this way, I'll be moving this way. So the direction reverses. So the important takeaways are, output contracts, direction reverses, so this character does not change. Next example, by now some of you will have guessed. So here we go again with our circle. Sorry, let me make this bigger. And when we draw this,
So what is the
things will
function ls?
just consider right now as any function, complex function. Later on, it will take the place of your GSHS. Okay. We are just studying the behavior. We have not applied yet. We have talked about how this can be applied, but we have not applied this yet, the ideas. So in this case, this is my origin. And how will this thing look like? This will be, actually you can substitute a complex number. Z is equal to S minus 4, and it should be, therefore, just like before. And you can simplify and work things out. I'm just giving you the output plot, how it should look like. It will look large. It will have a radius 5 because I'm putting in this 10 out here. So that multiplication by 10 will result in a reasonably large circle. With the origin out here. You can check this out yourself by drawing it. Right now you have to trust me. So this is how it's going to kind of look like. And as I said, if you move this way, in this case, you will move this way in this case. So we again have direction of traversal is reversed. Oh, sorry. So our biggest takeaway is origin is not enclosed. You can easily verify yourself by plotting these things, maybe using MATLAB. And that sense of direction, yes, if I move this way here, I'll move this way here. So now I'll show you a couple of videos explaining the same things. Oh, this is for the multiple pole, sorry. Yeah, so this is for the poles. Yeah. So this is a kind of a summary. Observe the videos. This is for the first example. Okay. So the angles are there, same angle, same direction, and this whole thing gets completed. Next example, shifting. Because we have now a pole at s is equal to -4. This is what you are going to see. -6 is this. Okay. Um, this is when we have the poles. See, this is how we start when we are having the pole at 0, we are traversing in the opposite direction. Complete. Second case, observe the position vector. When you are close to the pole in the contour, input contour, you are getting farthest away in the output, the closer you get, because of the reciprocal thing. You have a 1 by S. This is when you are considering -6 as a pole. But that basic behavior remains the same. The closer you get in the input side, the further you are on the input side, the closer you are on the output side. Again, because of that reciprocation. For the input side and the output side, I am talking of the pole. In the input side, it is the pole in question, and the output side, it is the origin. And finally, this is an interesting example. Here, where is the pole? Look on the right side, you will see that the pole is at around 4.8, 4.9, very, very close to the edge of the contour. And in this case, as you get very, very close, the 1 by, you have a 1, in that case 1 by S plus 4.8 in the denominator. So when you put S is equal to -5, what is going to happen? It is going to get very, very close to a very high value. So when your pole actually lies on the contour, things go to infinity. This is an important concept because this is kind of going to help us what is going to happen when we are going to deal with poles that lie on the imaginary axis. When we are going to consider, if you consider a unit semicircle, then we are going to pass very, very close to a pole which say lies at the origin, or to a pole which lies on the imaginary axis. So when that happens, things will blow up in the plot. This behavior shows that. I'll repeat again. We come close to the pole, things blow up. We get further away, things get back to normal. Okay? We come back from the infinities, we come back to a tangible zone. And now, arbitrary curve. Even then the same thing remains valid. This of course you have to trust, but you can, I mean, like, select your arbitrary curve and do this plotting. This is for Ls is equal to S kind of thing. And When you are dealing with a pole, earlier we were dealing with a zero. When you are dealing with a pole, then of course the opposite happens. And here is what happens when you are dealing with a pair of complex conjugate zeros or poles using an arbitrary input curve. Look at those faint lines that you see. Let me pause here. See, these faint lines, what do they correspond to? They are the S plus pi vectors. These are the angles and these are the magnitudes. Okay? So now what happens when you have a contour, a closed contour, when a single pole traverses, when you are having a function with a single pole, then, or a zero, then it is going to contribute that S equal to e to the power I theta. Let us say we are dealing with an input circle. When you have a single pole or S, then what happens? Let me get back to my OneNote for a minute or two to explain this idea. Through a simple example. What about, let us say, multiple zeros? Let's say I'm taking my input contour as S is equal to 5 e to the power I theta. Ls is equal to S square. So what is Ls? So what will be the change in behavior in this case? In this direction. Here also the movement will be in the same direction. the phi will be equal to 2 theta. So when you have two poles, two zeros, you are going to see two traversals over 2 pi. Your input contour, close contour, you traverse fully, your position vector about the origin is going to rotate through 0 to 2 pi. Your output plot, the position vector of a point in that case will move through 0 to 4 pi. Magnitude we are not bothering about, but this is bound to happen. Similarly, poles are more than one. Simplest example, let me make this 10. Oh, okay, I'll keep it as 1 itself. Emphasize the point. So this will be uh, 1 by 25. That means 0.04. So if you traverse in this direction, in this case, and you'll have this angle phi. From 0 to minus 4 pi. So in this case, the direction of traversal will be like this. Okay. So if you have more poles, you'll have more. If you are moving clockwise in your input, when you have zeros, you will move clockwise in your output, and the angle traversed will be clockwise into the number of zeros. If you have that, you are enclosing. If you are having poles, then it will be, if you are moving clockwise, you are going to move counterclockwise in your output, and the number of times you enclose your origin will depend on the number of poles that you are enclosing. So one is in the positive sense, another is in the negative sense. So here we are. When we are moving like this, arbitrary contour, we are seeing this for a pole, and when we are considering complex conjugates also, you will see that the behavior, if you plot, the behavior is very, very similar. Only thing is, as you get close, when you get close to a pole, you move very far away from the origin. As you move away, you are coming closer to the origin. Second pole again, move close, you are here. Moving far away. Now, how much is the traversal? In one case, we have overall, we have moved through 0 to 2 pi. Here, if you look, you have moved through 0 to 4 pi. Visually, you can see two distorted circles and connected circles, of course, because it's actually a closed curve. And where are your poles? Your poles were outside your contour. Consequence, in your plot also, the poles are outside the contour. If your poles had been inside your contour, then you would have enclosed the origin twice. See, it came very close to the poles. Here, when it came very close to the poles, the input was very close to the poles, the output, look carefully, the output was trying to enclose, getting closer and closer, but did not. Second pole also, another attempt, getting closer and closer, see, but did not. So the enclosure of the origin and the number of times the enclosure takes place is dependent on the number of poles and zeros which are enclosed by the input contour. So this is our basic takeaway for today. And as I said, the bad poles lie in the right hand plane. So it's like, I mean, like, how would I say, you have, say, something like somebody has called up the police and said that there are certain explosives in this building. So how do you detect it? You go around with a probe outside the building. So here my building is the whole of the right hand plane. So therefore, sorry.